Welcome to the presentation on number of ways to form a target string problem. Today we will walk through the approach to solving this interesting problem. Let's get started. The problem presents us with a list of strings where each string has the same length and a target string. Our goal is to find the number of ways to form the target string using characters at the same position across all strings in the list. The result is required modulo 10 to the power 9 plus 7. The input sizes are manageable enough for us to apply a dynamic programming approach. Before diving into the solution, let's note a few key observations. First, characters at the same position in the input strings can be reused to form the target string. Second, we need to efficiently compute the number of ways, which means we will pre-compute character frequencies. Finally, we will rely on dynamic programming to store intermediate results and prevent unnecessary recomputation, using modular arithmetic to manage large numbers. Here's the overall approach we will use. Step 1. We will pre-compute the frequency of characters at each position in the strings. Step 2. Using dynamic programming, we will define a state to track the number of ways to form prefixes of the target string. Step 3. Throughout, we will ensure that our calculations stay manageable by using modulo 10 to the power 9 plus 7. Step 1 involves constructing the frequency table. For each character and position, we will count how often each character appears at that position across all the words. This will allow us to quickly determine if a particular character is available when trying to form the target string. Now let's define our dynamic programming state. dpij will represent the number of ways to form the first I characters of the target using the first j columns of the words. The base case is simple. dp0j equals 1 because the empty target string can always be formed. The transitions are as follows. If we skip a column, we simply carry over the previous result. If we use the current column because it matches the target character, we update the count accordingly, multiplying by the frequency of that character at the current position. Let's look at the first part of the implementation. Here we define the function numWays, which takes the list of words and the target string as input. We initialize the frequency table and populate it by iterating through each word and counting the characters at each position. Now for the second part of the implementation, we initialize the dynamic programming table. We set the base case, then iterate over the target string and the columns of the words. For each position, we either skip the column or use it if it matches the current target character. updating the DP table accordingly. Finally, we return the result stored in dpmn, where m is the length of the target string and n is the length of the words. Let's go through an example to understand how it works. Consider the words A, C, C, A, B, 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 and C, A, C, A, and the target string A, B, A. First, we build the frequency table based on the characters at each position. Then we apply the dynamic programming approach to calculate the number of ways to form the target string. The result in this case is 6. There are 6 distinct ways to form ABA from the given words. Let's now analyze the time and space complexity of our solution. Time complexity. Pre-computing the frequency table takes big O of n times L, where L is the length of words. The DP computation takes big O of n times n, where m is the length of the target string. Thus, the overall time complexity is big O of n times L plus m times n. Space complexity. We use big O of 26 times n for the frequency table and big O of m times n for the dynamic programming table. To summarize, we have efficiently solved the problem of counting the number of ways to form the target string using characters from the same positions in the words. We leveraged the techniques of frequency tables, dynamic programming, and modular arithmetic to handle large inputs and constraints. This approach ensures we can solve the problem efficiently even with larger input sizes. Thank you for your attention. I hope this explanation was clear and helpful. If you have any questions, I will be happy to answer them now.